All right, so the next section we're going to take a look at has to do with the peculiar characteristics of water that allows it to be sort of the basis for a lot of what we know, what we understand about acids and bases. So when you have a sample of pure H2O, and that's or the only thing you have in that sample, something very interesting can happen. So there's a water molecule, and there's another one. We have two of these, and this is just representing two out of billions of them that would be in a sample of just pure H2O. What can happen is simultaneously in this sample, water can act as both an acid and a base. So for instance, this one here on the left side, it can act as an acid and we can lose that H plus. Let's say this one here loses that H plus. So this is going to act as an acid. Well, where is that H plus going to go? The only place for it to go would be to the H2O on the right here. So this is going to accept that H plus. So this is going to act as a base. And when the black now, H2O, when that loses an H plus, what does it become? Well, if we take away, right, this H plus in yellow, we end up with OH with a minus charge. And then if we take that H plus and we stick it onto the blue water molecule, well, then we end up with OH, H. And then we have a new bond to that H, and then this entire thing is going to have a positive charge on it. Right, so again, what we have here now are conjugate acid-base pairs. So we have this H2O here acting as an acid, loses an H plus, it becomes the hydroxide. This is going to be the conjugate base. And then the other one, this one here, acting as a base, accepts the proton, it becomes H3O plus. That then will be the conjugate acid of H2O. Okay, this reaction happens in water. It doesn't happen a lot, but it does happen, and that's the key thing. And because it doesn't happen a lot, it actually happens in equilibrium. And because the water itself is able to form these ions, and we'll just briefly um, condense their structures there. So the OH obviously is the hydroxide, OH minus ion. The O and the three H's, this is a H3O plus, the hydronium ion. Right? So the fact that water can form water itself to form these two different ions in solution means then that this is referred to as an autoionization of the water. It's able to ionize itself. Okay. So we end up forming these species, the OH minus and H3O plus are present, but they're present in the very, very, very small amount, very small concentration. Okay, so this is what happens in the case of water. Whenever you have water in something, it's going to act this way. Water itself is behaving as both an acid and a base, or either an acid or a base. They refer to it as amphoteric species. It's something that can behave as both an acid and a base. Because this is an equilibrium system, right, we can write an expression for this. So if we have now our H2O, let's just rewrite this plus H2O. I drew the structures on top so you can actually see where the things are going. So this is the cluster that we moved from one water molecule to the other one. This happens in equilibrium. We end up forming the OH minus, AQ, and then we have the H3O plus, AQ. Okay, so we can write an expression, equilibrium expression for this. If we have the products times each other, concentrations of those, and then we'll divide it by the reactants. But remember now, when we write these expressions, we typically don't have concentrations of solids or liquids in the expression because those concentrations don't change. In other words, the constant. If we take this and move it over here to the left side, right, we end up with our K times H2O squared is equal to OH minus times H3O plus. If this entire thing now is going to be a new constant, because K is a constant. Concentration of water, liquid, is also going to be a constant. So this is a brand new constant that we're going to call Kw, and that's equal to OH minus times H3O plus. Right, so this is the equilibrium expression then for the autoionization of H2O. And the K that we've seen before in our equilibrium section, we have the subscript now W. The W here, this means it's specific. Okay, so we're applying some of that equilibrium stuff to this section. Now, in pure water, just have nothing else in there. The concentration of the OH minus is exactly equal to the concentration of the H3O plus. All right, and that is themselves are equal to 1.0 times 10 to the minus 7 molar. So what this means is when you have water, sample of pure water, this reaction here happens. It doesn't happen a lot. It happens very infrequently, but it does happen. That's the key thing. And the concentrations of these, the hydroxide and the hydronium, these are exactly equal to each other. And those concentrations are 1 times 10 to the negative 7 each. So if I substitute these values now into this equation, I end up now with Kw being equal to 1.0 times 10 to the minus 7 and 1.0 times 10 to the minus 7. So okay, this is going to give me 1.0 times 10 to the negative 14. This is known as the ion product of water. And this is specified at 25 degrees Celsius. Because as we know, equilibrium can be temperature dependent. Kw here is just a specific example of the Kc expression that we've used before. Okay, so this is the ion product. We'll just be more specific. Ion product constant of water, which means that number doesn't change, right? You multiply the OH minus by the H3O plus, we're always going to get 1 times 10 to the negative 14. In the case of pure water, those concentrations are exactly equal to each other. So what this means then is that we can use the concentrations of the OH minus and the H3O plus to describe our solutions. So when you have the OH minus concentration being exactly equal to the H3O plus concentration, we say that that solution, whatever that solution is a neutral solution. If the OH minus concentration is less than the H3O plus concentration, the hydronium, we say that that solution is acidic. And if the OH minus concentration is greater than the H3O plus concentration, we say that that solution is basic. Sometimes we see the term alkaline. Okay, so we can define 3 different types of solutions based on the relative concentrations of hydroxide and the hydronium. Now, remember, this is very important. The H3O plus, the hydronium, is the same as the proton, H plus. Okay, they're used interchangeably. They refer to the same species. One is just more efficient to write because there are fewer things to write, H plus, as opposed to the H3O plus. Okay, so I will use them interchangeably as well. They mean the same thing, right? You'll see that in your textbook also. So if we have our OH minus and H3O pluses, we can compare their concentration to define or describe our solutions. So let's take a look at an example involving some calculations. So on the left side here, we have, or we're told that the concentration of hydronium ions in the stomach is 0.10 molar. Calculate the concentration of hydroxide at 25 degrees Celsius. All right, so you're given the concentration of hydronium as 0.10 molar. H3O plus 0. And what we need to find here is the concentration of hydroxide. We don't know this. So we need a relationship between these two. Well, the only relationship is our Kw expression, right? So we have our Kw being equal to OH minus times H3O plus. And obviously, doing a little bit of rearrangement here, the OH minus concentration would be equal to Kw divided by the H3O plus. And all we need to do is take our values, substitute them into our equation. Okay, it just becomes an algebra problem after that. Yes, we're using scientific notation, etc. So you need to pay attention to how you enter your numbers in your calculator. But really, it does, like most of the other things we've done so far, boils down to math that we're doing. Okay, so you should be able to rearrange this equation fairly quickly to solve for any of those unknowns. And once you get your values, right, you can compare them according to this very short table here to see whether that solution is acidic or basic.